Cluster analysis is the generic name for a wide variety of procedures that can be used to create a classification. The procedures form groups of highly similar entities. It's basically a factor analysis on people as opposed to on responses. It reorganizes large data sets into entities with relatively homogeneous groups. It's used for four goals. One goal is development of a typology or classification. Another is investigation of useful conceptual schemes for grouping entities. Hypothesis generation through data exploration. And also for hypothesis testing, or the attempt to determine if types defined through other procedures are in fact present in a dataset. So for my cluster analysis, I am looking at what groups of people are more likely to leave the organization, so intention for turnover. My variables of interest are right here, and they are sex, race, performance ratings, age, distance from work, number of children, full or part-time status, and years of experience. And I have 1,000 different people in my data set. And my turnover variable is actually external to my data set. So each line represents a person, and these are the predictors, and then my turnover, which is my outcome, is actually not included in this, it's external. So I first installed these necessary packages. The main ones used were tidyverse, which is for data manipulation, cluster for clustering algorithms, and factoextra for clustering algorithms and visualization. I then libraried them for additional use in the future. I also attached my data set to the script, so that's what I did right here. We're going to have to go here since I haven't done this since yesterday. So once again, we're now going to attach it. Alright, it works. You'll see it in my outcome. Anyways, then I created all the factors. So, sex, female was a 1, male was a 2. For race, 1 is African American, 2 is Asian, 3 is Hispanic, 4 is other, and 5 is white. I did not tell R the number to assign each category, so it did in alphabetical order. Performance ratings were a variable of 1 to 5, depending on what the participant received. Age, number of children, and years of experience were all continuous variables. And for full or part-time hours, 1 was full-time, 2 is part-time. So then I checked to make sure that it was created correctly. Then I omitted any missing data, and then I standardized, standardized the data as well. I then created the model. Well, I checked to make sure it was standardized. There we go, it's standardized. I then created the cluster model to be run, specifying that there should be 2 clusters. I looked at the attributes and number of centroids next. So we're going to go through and run this code real quick. And that's just developing the model, and here we're going to run it. And we look over at this model and see where it curves, and it curves at 2, so that's how I knew right here to actually set my cluster amount to 2. So I run it. Now I'm going to get the attributes, and then I get the center, and that's the number of centroids. Then I look at what cluster each person is in. So this has all 1,000 people, and if they're assigned to either cluster 1 or cluster 2. I then can look at the cluster size. So there's 512 people in cluster 1 and 488 people in cluster 2. I then created the formula for the model to run the statistics. It compares the clusters to randomly produced data for validation. So I'm just making sure that my clusters are actually different in what they predict. This is necessary since my outcome variable of interest is actually external to my data set. The procedure is similar to a Monte Carlo simulation. So I then ran the model, which is used to measure how close clustering is to predetermined benchmark clusters, or classes, excuse me. So this is where we create it, and here is where we run it. And you actually want a higher done report. which is what we just ran, it done index, because it means that there's better clustering in your data set, which is essentially that the clusters are compact and they're separated from each other. They're measuring two different things that separate them is what it's amounting to. Well, they're measuring the same thing, but for instance, like part-time might go into one and full-time in another. The next line reports the cluster statistics when compared to another data set. It reports statistics we saw before, like the cluster size and number of clusters, but it also provides more info like the diameters of the clusters and average distance, among other descriptions. So once again, what I was just explaining, number of clusters, size of clusters, minimum cluster size, diameter, average distance, median distance, has a lot more information than we've seen before. I then once again tried to validate my cluster findings again. It ran perfectly, and then the session aborted, and of course it no longer works, but here is the correct code. So I'll show you what my clusters look like. Those are my clusters. They're absolutely horrible. Then we're going to build the matrix, and then we are going to create the comparison group like we did before. Oh, that's not my one. Here. Like we did before, and this is where it's not running. So that's what would have run. It would have compared it. This is the correct code for the RAND index, and then the Mila's VI is also next. So the adjusted RAND index computes similarity of all pairwise comparisons between the clusters created by the clustering algorithm to benchmark classifications like we did before. It provides a measure of assessing the similarity between two clusters. It's adjusted for chance from no agreement to perfect agreement. Then the Mila's VI, which is that last line of code, compares the two clusters, providing variation in info or the amount of information gained and lost between the two clusters. So now let's look at my LPA, which is over here, and we're just going to go ahead and import that data set as well. So, Cranston School, class name, PA, data, import. Alright, so there's my data. So LPA, or latent profile analysis, aims to recover hidden groups from the observed data as well. They are a flexible clustering technique based on an explicit model of the data, so it allows you to account for the fact that the recovered groups are uncertain. LPA tries to recover hidden groups based on the means of continuous observed variables. So my organization is planning to have a community in-service day, and I asked each participant to rank 5 activities, and I'm using the data to predict how many people will be interested in each of my community service activities that are actually going to be offered on the day. You know, I'm really big into HR. I'm kind of taking on the HR role as opposed to the IR role. IO role, goodness. So the participants ranked playing at dog shelters, working at nursing homes, doing yard work, washing cars, and painting. Like before, each line actually represents a person, and this is what they preferred. So I attached my data set. It's already been attached, so it's doing this, but anyways. Here's my packages. I install them and I library them. I then begin creating my model. So I'm omitting missing data and standardizing the data like I did for the clusters. I create the model for the clustering of interest and I plot it right here. So there it is, and I'll just go ahead and admit that my data sets are exactly equal, so all 5 of the categories have the same number of people, and so it messes up everything from here on out. But we would be looking to see one group doing like this, and then another like this, and another like this, so they would all be different. And we would be looking at see the number of people in each and the route that they take to get down. So then when we do the summary, it actually reports the top 3 models based on the Bayesian information criteria. And since all 3 of my clusters are the same in relation to variable volume, variable shape, equal orientation, and ellipsoidal distribution, as you can see here, they're all identical. But typically they would be, EE would be 2 numbers, EEV would be 2, EVE would be 2, it would be different. And these would be the 3 highest. So I then create a new model based on what would have been the best model reported in the summary. But since mine were all the same, I just chose one of the 3 to continue with. So I chose EEE, but I could have chosen any of these since they're exact same. But typically you would choose the best one to continue. So then I run it, and I create the output, which describes the geometric characteristics of the profiles and the number of cases classified into each cluster. Well, mine once again isn't very good, but anyways. I then took the means from all 3 models, which in case mine were the same. And so this is where I'm taking the means. Now I'm going to plot it. So typically when I plot it, if significant differences existed between each of my cluster groups, they would show the dots in different places on my graph. But since mine's just one group that's all the same, it's right here. But typically you would have the 3 dots. So that is my LPA. So long.